right, guys. So this video is recapping free fall that you learned on Wednesday with your lab and Thursday for the lesson. Okay. So free fall, if you switch it around, you're dealing with objects that are falling freely. And when we think about objects that are falling, we think about gravity, especially with us on Earth. Okay. And then also the good thing about free fall and the equation that you use, we're going to use the same equation in the next video when I explain how to solve problems using big equation number 2. So before we get into that, let's look at this free fall problem. We have a feather that is dropped on the moon and on Earth from a height of 1.40 meters. The acceleration of gravity on the moon is 1.67 meters per second, and we are going to determine how long it takes the feather to hit the ground on the moon and on Earth. So let's work backwards. What is the problem asking us to solve? Well, when you see determine how long it takes, we're thinking about time. Same thing if you're trying to go out with your friends and you want to know how long will it take for you to get ready, you're looking at the time. So here, once again, I have the 5 symbols listed. I'm going to put a question mark on time. They tell us that the acceleration of gravity on the moon is 1.67. So my A for the moon is 1.67. And since the object is falling, we have to think about the direction that it's falling. If we're falling, we're going down. So that means my acceleration on the moon needs to be negative. Now, the question wants us to consider how long it takes for the feather to hit the ground on Earth as well. But what does our acceleration do to gravity on Earth? That beautiful number that you're going to see so much of, negative 9.8. So that should let you know we're going to be doing solving for 2 answers. Okay? The feather on Earth and on the moon was dropped from a height of 1.40 meters. Well, you guys are used to seeing D for distance. I understand. However, our units is meters. We're still measuring some type of length. So therefore, our height is also our distance. And then the one thing about free fall that you also need to always remember, we have to think about gravity with free fall, and then our beginning speed is always 0. And this is when we are talking about objects falling. You see right here, my beginning speed is 0, and then I drop it. Same thing if I was to throw my object up, my initial speed is 0 before I throw it up, okay? The only variable that doesn't have anything that we are now considering is final velocity. So since BF is left blank and alone, it won't be considered. So hopefully by now you're picking up on a pattern with out of the 5 variables, 4 of them would be considered. And of these 4 variables, we know which equation to use because we have a distance, we have our beginning speed. Even though we don't have a number for time, we have to include time, and then we also have our acceleration. Okay, so now we're gonna take our information and we're just gonna plug it into the equation. So my D is 1.4. Okay, let me split this up. We're gonna have our moon side and our earth side. Because the question is asking for the time it takes the feather to fall on both locations. So my distance is 1.4. My VI is 0. We don't know our time, so we're going to keep it as T. Plus 1/2, and that stays the same. Our acceleration on the moon is negative 1.67, and on Earth is negative 9.8. And there we have our T squared at the end, because remember, we're still looking for time. Also, one more thing I did forget, because we are dropping the object, we had the negative acceleration. We also have the negative distance or negative height because it's falling down. Now let's solve for time for the moon. First things first, anything times 0 is 0. So now I have negative 1.4 is equal to 1/2 times negative 1.67 times T squared. I'm grabbing my calculator. I'm going to take half of negative 1.67. I'll bring this down. I will get negative 0.835, and I still bring down my T squared. We are multiplying this number times the T squared. So the opposite is dividing. And now I will get 0 divided by 0.835. So what we'll get for T squared, once we divide, you get 1.68. We are not finished because we need T and not T squared. So the opposite of taking the squaring something is taking the square root. So the square root of my answer, I'm gonna do just 1.68. I get 1.30 seconds as my time. It takes 1.30 seconds for that feather to fall on the moon. Now we want to do the same thing and get the time for Earth. Negative 1.40, same height, half of 9.8. Divided by 2. We get 4.9 times t squared. We're multiplying by 4.9. Oops, that should be negative. Caught my mistake. Why? Because we have that negative 9.8 that we took half of. We're going to divide negative 1.40 divided by negative 4.9. T squared is 0.29. We are not finished because we need to get rid of this exponent. Opposite of squaring is taking the square root. So on Earth, our time is going to be 0.54 seconds. So for free fall, you will always have your acceleration due to gravity. And for Earth is always 9.8. But you may be on a different location and you may be given a different acceleration number. And your initial velocity is always 0. So you can always cancel this part out of your equation number 2. So yesterday you seen D or H is equal to 1/2 AT squared, or that A was probably a G, and G stands for gravity, which is the numbers that we had in this problem.